Now that you've heard a brief discussion of weak acids, let's talk about buffers. A buffered solution is a solution that can resist a change in pH when an acid or base is added by neutralizing the added acid or base. There are two components to a buffer, as you must have one component that would neutralize the addition of a base, and you must have another component that would neutralize the addition of an acid. Therefore, a buffer consists of either a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. An example of a good buffering solution is acetic acid and sodium acetate, with acetic acid being the weak acid and sodium acetate being the salt of the conjugate base. The buffering system resists changes in pH by absorbing or neutralizing any acid or base that is added to the system so that there is no significant change in the concentration of hydrogen ions or hydroxide ions in the solution. Assume the buffering system is composed of HA, the weak acid, and A-, the conjugate base, that appears in the center of the diagram. If an acid is added, that's essentially the same thing as adding H+. So the H+ would combine with A-, the conjugate base, in order to make HA. You can see here that the acid, the H+, would combine with the A-, the conjugate base, in order to make HA. In this way, the acid is essentially absorbed by the buffer so that it doesn't cause the pH of the solution to change. If a base is added, that's essentially the same thing as adding OH-. So the OH- would combine with the H+ from the weak acid. You can see this here. The OH- would combine with the H+ from the weak acid in order to form water and leave the A-, which is the conjugate base. In this way, the OH- that could change the pH of the solution is being absorbed by the H+ from the weak acid in the buffer, preventing the change in pH. Why is it that a buffer can't simply be a weak acid or a weak base, but that it must be the weak acid and its conjugate base, or the weak base and its conjugate acid? Why not just have one of the components? Let's evaluate the buffering capacity for a weak acid alone, without additional conjugate base added. If a buffer were made up of only acetic acid, the buffer would contain a lot of acetic acid and only small amounts of H+ and the conjugate base, the acetate ion CH3COO-. This would be a good buffer against the addition of base, as the base would combine with a small amount of H+, causing more acetic acid to break down. Because there is so much of the acidic component, it can continually break down into H+ and the conjugate base in order to neutralize the added base. However, it would be a bad buffer against the addition of acid, because there is not much conjugate base around for the acid to combine with in order to be neutralized. If the buffer system consisted of equal amounts of the acetic acid and the conjugate base, the acetate ion, as seen in the middle of the diagram, acetic acid and the acetate ion, the addition of acid would be buffered against, as the H+ would combine with the acetate ion in order to form acetic acid, and the addition of base would be buffered against, as the OH- would combine with the H+ from the dissociated acetic acid in order to form water. Let's consider the buffering capacity of a weak base alone, without equal amounts of its conjugate acid. If a buffer were made up of only ammonia, a weak base, the buffer would consist mainly of ammonia and only small amounts of ammonium and hydroxide would be present. This would be a good buffer against the addition of acid, as H+ from the acid being added would be neutralized by the OH- that came from the ionization of the ammonia. However, it would be a bad buffer against the addition of the base, as there is not much conjugate acid around for the base to combine with in order to be neutralized. If the buffering system consisted of equal amounts of ammonia and the ammonium ion, as seen in the middle of the diagram, the addition of base would be buffered against, as the OH- would react with the H+ from the ammonium to form water and ammonia, and the addition of acid would be buffered against, as the H+ would combine with ammonia to form ammonium. The Henderson-Hasselbalch equation is useful as it relates the pH of a buffer solution, the Ka of the weak acid making up the buffer, and the concentrations of the buffering components of the solution. We can derive the Henderson-Hasselbalch equation by starting with the equilibrium expression for a buffered solution. Ha, the weak acid, dissociates into H+ and A- the conjugate base. Writing the Ka for the solution, we get the following. Ka equals the concentration of H+ times the concentration of A- divided by the concentration of Ha. In order to get pH into the equation, we take the negative log of both sides to get negative log of Ka equals negative log of the quantity of H+ times A- over Ha. Rearranging the expression, we get negative log of Ka equals negative log H+ minus log of A- over Ha. We know that the pKa is equal to the negative log of the Ka, and we know that the pH is equal to the negative log of the H+. So after simplifying, we are left with pKa equals pH minus log of A- over Ha. Keeping in mind that Ha is the weak acid and A- is the conjugate base of the weak acid, we can more generically write the equation as pH equals pK plus log of A- over Ha. More generically, this can be written as pH equals pKa plus log of the concentration of base over the concentration of acid. Keep in mind that the base that this is referring to is the conjugate base of the acid. Note that if equal amounts of the acid and the conjugate base are present, the log of base over acid becomes 0, and the pH of the solution will equal the pKa, because the log of 1 is 0. If the ratio of base to acid is 10:1 or vice versa, the pH will still be within 1 pH unit of the pKa. The implication of this is that a good buffer contains roughly equal concentrations of acid and conjugate base. You may remember from chemistry that a titration is used in order to determine the amount of acid or base in a solution of unknown concentration. In general, a measured volume of the acid is titrated with a base until all of the acid has been neutralized. At that point, the concentration of the acid can be calculated as long as you know the concentration and the amount of the base that was used. We can draw a titration curve for the titration of the weak acid, acetic acid. Note that pH is on the y-axis and hydroxide equivalents and percent titrated are on the x-axis. When you first start the titration and no base has been added, almost all of the acetic acid exists in its non-ionized form. As base is added, it is neutralized by the H+ in the solution. As free H+ is removed, more acetic acid breaks down into H+ and acetate, as the H+ continues to get neutralized by the base. At the midpoint of the titration, when 0.5 equivalents of base have been added to the acid, there are equal amounts of acid and conjugate base. As we just saw in the Henderson-Hasselbalch equation, note that at this point, when the amounts of acid and base are equal, the pH of the solution is equal to the pKa of the solution. As more base is added, even more acetic acid breaks down until eventually all of the acetic acid has been dissociated and it only exists as the acetate ion by the end of the titration. The pink area on the graph indicates the buffering region, which you will notice is within 1 pH unit of the pKa, meaning that there is up to 10 times as much acid as base, or vice versa. In the buffering region, the curve is flattened out, whereas at the beginning and the end of the titration, the curve is very steep.